All right. Hopefully there's no confusion about today. I know we've got dialogue days going on. Even for some of my classes I've canceled, but I think for us, I want to make sure we're kind of keeping up so that this next exam, we have, just a little bit more time to kind of cover things. So we left off, and I think I kind of quickly went through this example where we were building a confidence interval. So I kind of refresh our memory on what we were doing there. We'll talk about one of the things, and then we'll do quite a bit of work in Excel. So what we were doing, right? And we kind of went through the justification for why this is the case. But if we want to do a 95% confidence interval, we know that if we take the sample mean value we see, and we go a certain number of standard deviations away from that, and that depends on what level of confidence we want to say something with, right? We knew that if we want to say something with 90% confidence, right? 90% of the time when we build a confidence interval in this way, it will include the true population mean. 10% of the time will be wrong, but 90% of the time will be right. And then if this is the number of standard deviations away that we want to go, we said, okay, we need to multiply that by the value of the standard deviation. So another way of writing this, we know that the standard deviation of our sample means is simply the square root of whatever that population variance is, the variable we sampled from, divided by the sample size. So it's kind of where we left off. So really the only tricky part of this, I mean, in every problem, you're going to have to be told what that population variance is. There's no way that you would just be able to know that. All right, so these problems seem a little weird at first, but then we'll transition kind of probably Friday and next week to what happens when we don't know the population variance. From our sample, we know our sample size and we can calculate our sample mean. So notice these three things, I mean, in practice, we would be calculating this, right? We can observe, we can see what the size of the sample is, and we're told that population variance. The only thing we really have to find is the number of standard deviations away from that sample mean we want to go to build our confidence. So we said the way we do that, right, is if I've got, we kind of thought about the distribution of my sample means. We want to go out a certain number of standard deviations such that alpha total was in the tails, which means that we've got two tails, alpha over 2 would be on each tail. Right? So that's why it kind of says the z-score that gives us alpha over 2 kind of in both of those tails. So we went to what I forgot to pull up, our z tables, our standard normal tables. Since someone's already done the work for us, we look up that value of 0.005 in the middle because it's a probability, it's the area in the tail that we want. Looks like we're in between these two values. So the z-score that corresponds to the probability of about 0.05 is negative 1.64 and negative 1.65. So, I said in practice, what we'll do is kind of use the larger and absolute value, or we would use 1.65 here. Right? And that negative sign, when we look up alpha over 2, it's always going to be a small area. So we're always going to have a negative z-score, right? It's going to be a probability that's closer to 0. But that positive and negative, it's already built into our confidence interval equation, where when we add or use the positive z-score, we're getting the upper bound. And when we subtract that value or use the negative z-score, that will be giving us our lower bound. So that negative sign will always be in front of it. We kind of ignore it, right? Because we know it's already built into our confidence interval equation. Okay? Does that make sense? Okay. So, so that was kind of the example we left off on. We just identify the piece of information. I guess identifying alpha, we have to start getting used to that. From the 90% confidence interval, we said alpha is essentially the area outside the interval in decimal form. So 10% would be outside of my interval, in decimal form, 0.1. Right? If I wanted the 99%, area outside would be 1%, in decimal form, 0.01 would be alpha. Okay. So once we looked up that z-score, right, now it's just a matter of plugging everything into our equation. You can calculate the standard deviation of your sample means, like as an intermediate step if you want to. That's kind of how you would have to do it, to use this first equation on the board, or you can do it all at one time, right? Kind of all built into the same formula. I usually, say in practice, it's good to kind of do that intermediate step. It just starts to kind of give you an idea about how many standard deviation, what a standard deviation is for the sample mean that you're looking at and for the specific sample size. It also allows us to kind of think about, right, how the width of our confidence interval is being influenced by these different factors. When I take a really, really high sample size, what's going to happen is, well, we know that that drives down the standard deviation for my sample means. Taking a larger sample just kind of guarantees that if I only have one sample, it's more likely to be a value centered around whatever the true mean is that I'm not able to observe. So by driving down that standard deviation of my sample means, if I want to do the 95% confidence interval, I'm always going, I think, 1.96 standard deviations away. If I want the 95% confidence interval, I'm always going 1.65 standard deviations away. So this number wouldn't change when I'm taking a higher sample size. So by driving down that standard deviation, I'm just creating a narrower and narrower range of values for being able to tell you the true population mean is somewhere in this range. If I can provide you a much smaller range, but I'm keeping the level of confidence the same, right? That alpha is not changing. That's a good thing. It allows you to be able to kind of pinpoint down where this true average is with just one sample. Right? So that's kind of the broader sort of picture kind of discussion. And sometimes seeing that intermediate standard deviation calculation helps a little bit. Also, it just makes it so you don't make as many mistakes on your calculator. Right? There's not as many moving parts. We kind of talked about how we could use this, right? In the example of this 45-pound weight plate, we could basically go to the company and say, look, based off the sample we took, which wasn't even that great of a sample, 35 isn't the biggest sample size. I can tell you that with 95% confidence, you're not hitting your target kind of weight for this product. Any questions on that? Kind of a little bit of a recap of where we were at. We're going to kind of think about, we've got all these different confidence levels that I already discussed, from the confidence level, I can determine alpha. From alpha, I can determine the confidence level. We should be able to work both ways there. But if I can do a confidence interval for a sample mean, I can also do a confidence interval for a sample proportion. So just to kind of refresh our memory, right? When we were looking at the sample proportion, we said it would be centered around that true population proportion. This is something we can't observe. Just like we took a sample, found a sample mean, we weren't able to observe the population. We took a sample, calculated the sample proportion, we don't observe the population. But we know that it's distributed normally around this, whatever that true population proportion is. So we can do the exact same thing we did with the sample mean. Think about, okay, I know that 95% of my sample means are going to, 95% of the sample proportions I see will be within what, 1.96, I believe, standard deviations of whatever that true sample, whatever that true population proportion is. Right? So then I know whenever I take a sample, if I create this confidence interval around it, where I go 1.96 standard deviations away, 95% of the time, the confidence interval will include that true population proportion. Now, if I get a sample proportion like out here, and I build a confidence interval around it, notice it might fall just short of including that true. So I will be making errors 5% of the time. It's the same idea of what we're doing with the sample mean. So if I'm trying to build a confidence interval, let's try to think about maybe what that equation would look like. Well, I no longer looking at a sample mean, I have a sample proportion. So that's one sample, that's all I see. That's what I should be building my confidence interval around, right? Instead of adding and subtracting something to the sample mean, we now add and subtract something to the sample proportion. Now we're using the same, the same principles are applying. We still want to go out a certain number of standard deviations. Well, how many standard deviations out do we want to go? Well, that depends on alpha, depends on the level of confidence we want. But we would still find that z value the exact same way. But then now, the number of standard deviations way I'm going will be whatever the standard deviation is for my sample proportions, which we go back a couple classes, actually maybe the beginning of last class. We said we know that we can calculate this using this one. Now we're going to run into a problem here, right? Because remember, that standard deviation of my sample proportions was kind of dictated by whatever that true population proportion was. I can't observe that, right? So what do you think I could maybe do? Instead of using the population proportion, I don't have that. What would be a really good estimate for that? I'm going to have to rely on my sample, right? I'll use my sample proportion as that's the best, my best estimate of what that true population proportion is. So now that standard deviation of my sample proportions, we're going to have to approximate it. Okay? Now, as long as our sample size is over 30, it's a really close approximation. We should have a sample high enough where that approximation is going to give us pretty close to whatever the true population proportion was. And we can prove that to ourselves if like we had population data, took a sample, and then we could actually use the sample proportion for the true population portion. And we can see that if we go over sample size 30, those are going to be really, really close approximations of 30. They're going to be very similar values, or that this will give us a close approximation. So don't worry too much about this. This is kind of just saying that we need to make sure if we have something that has a low probability of occurring, we make sure we have a high enough sample size, right? Or something that is like a real high probability of occurring, that we make sure our sample size is great enough to get us over this value of 5. I'll never make you check that. It's just in practice. We had smaller samples. This starts to be a concern. In practice, we usually have samples in the, to be practical, in the thousands, right? Usually when we're looking at data sets, the big data is a thing for a reason, right? So we could almost have kind of built out what that confidence interval equation would be, just thinking about what we're actually trying to do with this confidence. And we're just looking at a slightly different statistic, but it's still the same principles. Any questions on this? So notice here, it almost becomes easier in the sense that like, I no longer have to be told the population variance, because I'm calculating the variance using this sample proportion. So this is where I said last class, I'll start referring to that thing that we add and subtract from our sample mean as the margin of error. Technically, you shouldn't really do that unless you're talking about a population proportion example, but it gives us a nice term to always refer to that. I mean, it's really the same thing. Right? It kind of makes it easier kind of terminology wise. So let's think about how we kind of an example we're going to do this. So there's this old 2020 poll that was asking people about the Affordable Care Act. So it seems like something that's been around forever now, but there was a time where this didn't exist and people were fighting for it, right? So they took this poll, they found 63 out of 81 people were in favor of healthcare that covered pre-existing conditions. If I wanted to build a 99% confidence interval, we kind of say, with 99% confidence, I can tell you that the nation as a whole feels this way about this particular issue, right? Somewhere within this range of proportions. Well, the first thing I'm going to need is my sample proportion, which would just be what? Yeah. Yeah, sometimes it's not easy. It's not just given to us. We have to calculate it. So it'd be what? 63 over 81. I'm also trying to use this free market. So that's what I'm going to build my confidence interval around, right? So 63 over 81. Whatever that ends up being. So it's what? 7/9, which is 0.78 if we round to the second decimal. Right? So I'll then add and subtract to that the number of standard deviations away that I need to go to get a 99% confidence interval. Well, 99% confidence interval, what would my alpha value be? Just, yeah, area outside the interval is 1% in decimal form, 0.01. Right? So my alpha is 0.01. So I'm going to try to find the z-score for 0.01 divided by 2, right, or 0.005. So this is where in practice, kind of make sure that you're looking at that value correctly. A lot of the times we're going to have an area of 0.05 in the tail, but sometimes we'll have 0.005. So go to the table, looking for 0.005. Looks like it's in between these two values. So negative 2.57 and negative 2.58. So here, just kind of building this as we go. Kind of use the absolute value, just use 2.58 because that positive and negative are already built into the composite equation. From here, we can calculate the intermediate step, right? So here we want to multiply, if this is the number of standard deviations the way we want to go, multiply that by the standard deviation of the statistic we're looking at. So I could calculate that ahead of time. That's just the square root of what? 0.78 times 1 minus 0.78 divided by my sample size of 81. Okay. So whatever this ends up being, I plug in, and now, right, I just got a simple equation I just have to enter into my calculator. Okay. Any questions on this process? If you have questions, it's not a bad thing. I actually usually kind of like them. All right. So we found the z value of that 2.58. From there, we calculate the intermediate value, which the standard deviation ends up being 0.046. And this is where we really have to start being careful when we're looking at these values. Our standard deviations start to get pretty low pretty quick, especially when we're dealing with proportions. So we can get some pretty narrow ranges. But remember, if I get a pretty narrow range, let's say the width of my interval is only 0.1. Well, that still represents a variation of 10%, right? So I could be saying the favorable views are somewhere in between 50 and 60%, right? So it's still a pretty wide range because all these proportion values really could be converted into percentages by just multiplying by 100, right? And that's usually how we speak about them. So we kind of continue through this. We actually end up with the values, and based on the sample we saw, we could say that with 99% certainty, the favorability of this Affordable Health Care Act, what it was really trying to do was cover pre-existing conditions. That was the specific question that they asked. That the general public was somewhere between 2/3 and 90%, 66 and 90% in favor of this. And so it's something that it's hard to get attitudes to be that much in favor of so that everybody kind of pulling for. So this would be, if I saw this as a politician, I'd say, well, this is something that people are going to back me up on, right? With 99% certainty, I know that the vast majority, more than 2/3 of people, right, because that lower bound is just about 2/3, right, would be in favor of this. Okay. Any questions on this? All right with this? So let's say we had a different example. I might have you guys work on this one for a little bit. I won't take it as points. I'm just going to want to give you an opportunity to kind of work through one of these, right? Kind of figure out maybe where you're having some pitfalls. So let's say, so this was, I think I used this, some poll for the 2016 election. Let's say that there was some poll and 912 registered voters in the US, 46% said they're voting for Clinton. So that 46%, that's your sample proportion. So you have to convert that right into a decimal. And we're doing these proportions, we need to use it in decimal form. So instead of 46%, my sample proportion would be 0.46. Right? I have to deal with that in decimal form. I want you to build a 90% confidence interval. All right. So from that, you can determine what alpha is. And then try to work on this and come up with what the lower and upper bound would be. Okay? So give a little bit of time to work on this one. So keep on working. I'll kind of just talk a little bit. I've gotten to certain steps and you can kind of help me out. So if I'm thinking about the 90% confidence interval, what would my alpha value be? 0.1, so that's easy enough. Now remember, that's the total area on either side of our interval. We have two sides, right? We have the area below the lower bound, area above the upper bound. So our equation even reminds us, okay, then you need to find the z-score that gives you alpha divided by 2 in each tail. So 0.1 over 2 is 0.05. So I look that value up in the middle part of my table. I think we actually already did that earlier in an earlier example. So if I do that, what z value do I find? Yeah, so my alpha was what? 0.1. So that z-score for 0.1 over 2, I find to be 1.65. From there, I've got everything I need. I just start plugging things into that confidence interval equation, right? My sample proportion was 0.46. I add to get my upper bound, I subtract my margin of error to get my lower bound. 1.65 was the number of standard deviations the way I want to go. The only thing left to do is really calculate this intermediate step, the standard deviation of my sample proportions, and then plug that in. So that was the square root of my sample proportion times 1 minus my sample proportion divided by my sample size, which was what? Yeah, so this should be what value? Did anyone come up with this? Yep.
0.0165.
So pretty low, right? So even though I'm going 1.65 standard deviations to the left and the right, multiply that by what the standard deviation is, that's a pretty small value. Okay? So I plug that in. And then it's just kind of a simple 0.46 plus 1.65 times 0.0165. And that will give you your upper bound. Yeah, is this a little bit off?
No, I just,
Oh.
why is the
6.5?
is it large enough?
Yeah, so right, technically it is. If we want like a visual of really what we're doing when we're looking up that z value, what we technically want is the z value such that the area below that negative z value and the area above that value but positive, that total area is alpha, right? So when I look up just alpha divided by 2, I'm always kind of looking up the left tail. So I'm always going to find that negative z value, but that was when I wanted to go that many standard deviations below, that gives me my lower bound. And when I want to go that many standard deviation above, that gives me my upper bound. So that negative positives kind of already built into that formula. It's almost like, this is kind of shorthand. I guess if you wanted to be like really technically correct and have it displayed in maybe a way that is a little more, I don't know if it's necessarily better, but you would write this equation out twice, once with the negative, once with a positive, to kind of reflect, I'm actually technically using two different z-scores, right? I'm technically using the negative z-score to get the lower bound and the positive z-score to the upper bound. Yep. Any other questions on this one? So if we go through, right, we found our z-score, calculated the intermediate step. Now it's a matter of plugging everything in. We have about 0.43 and 0.49 almost, right? So I'll kind of use this to kind of show you, and I guess this is an election year, and it's kind of far off in the past from when we were actually thinking about political polls prior to elections. But this is really all they're doing when they're showing you like election results, or like trying to predict, not election results, trying to predict election results. They're saying, okay, based off this sample we took, the true population proportion of people who are going to vote for Clinton, with 90% confidence, I could say that population proportion is going to be somewhere in between 0.43 and about 0.49, right? So she's going to get somewhere between 43 and 49% of the popular vote with 90% confidence. I could say that. Right? Well, that's a pretty big swing there, right? I mean, if we're talking about the percent of the vote you're getting, I mean, sometimes in this last election, right? Or I guess not this last one, 2016, the difference in the popular vote might be less than 1% or 2. Yeah.
Why would you ever do 90%?
So you could do the 99% level, right? That's ultimately what you'd love to like. Let me think how I can phrase this. So hold off on that question for like 5 minutes, and then I'll come back to it. I'll show you something else and I can explain to you why. So this is our 90% level, right? So I can pinpoint down, at least with 90% confidence, where the vote for Clinton is going to be. I could use the same poll of 912 people, and I find that 40% were planning to vote for Trump in 2016. So I build my 90% confidence interval here. I go through all the same steps. Find the intermediate value, I build it around the new sample proportion of 0.4. I find that about, the confidence interval for the proportion of people who are going to vote for Trump is somewhere between 0.37 and 0.42. Or I could say, the percent of people who are going to vote for him is somewhere between 37 and 42%. Right? So why is this interesting? Then we'll get to back to the question. So at the 90% level, and I actually should grab this, so I want to be able to go back and forth. So we had what? Clinton was, and I'm going to round these pretty bad, so 0.43 and about 0.5, sorry, not 5, 0.49. So this was, the true proportion for people who are going to vote for Clinton, with 90% confidence, we were going to say it's somewhere in this range. Then we had Trump, so his was what? Actually, this is where I probably shouldn't count. The 43.4328 was that lower bound. Right? If I look at Trump's, so 0.4267 was the upper bound, 0.3732 was the lower bound. So what that's saying is the true proportion of people who are going to vote for Trump is somewhere within this range. So the 90% confidence level, if I look at this, there's no overlap in these confidence intervals. So at the very most, like if I said worst case scenario, I shouldn't say worst, I'm not trying to make this political, but like in this scenario, right? Worst case scenario, Donald Trump ends up, and this wasn't 0.46, was it? It was 0.426. He ends up getting that upper bound, right? And so with 90% confidence, the true population proportion is somewhere in this range. Could be as low as down here, or it could be as high as all the way up here. And let's say Clinton gets, her true population proportion to be somewhere in this range of values. Let's assume it's exactly equal to what that lower bound was in confidence. Well, since there's no overlap in these confidence intervals, even if that was the case, with 95% confidence, I can then say Clinton's going to end up with a higher proportion of the popular vote than Trump. Right? Because even if I look at the worst case scenario where these two things are at their extreme, they still don't overlap, that population proportion for Trump would still be below that of Clinton. So if there's no overlap in our confidence intervals, we can start to make some interesting statements. Now, if they do overlap, so let's just assume for a second, it looks something like this. All right, so here's Clinton. We had Trump over here and the proportion. Okay. If this was the scenario, well, it could be that the true population proportion for Clinton is somewhere over here, and the true population proportion for Trump is there. In that case, Clinton would be getting a larger proportion or percentage of the votes. But it could be that Clinton's true population proportion was somewhere down here, and that Trump's was somewhere up there, right? In which case, Trump would be getting a higher proportion, a higher percentage of the vote. So if there was any overlap in our confidence intervals, we can't really say anything with 90% confidence, right? Because we know with 90% confidence, there's somewhere in this range, but because they overlap, we really don't know which one is going to be larger than we actually know, or if we were able to actually observe the true population. Does this make sense here? Any questions on this? So back to the question finally, right? With 90% confidence, I can say Clinton is going to get a higher proportion of the vote. Right? What happens if I want to do this with 99% confidence, right? Better if I can say something with 99% confidence, right? That was kind of what we were getting at. Right? Why wouldn't I just say with 99? Well, if I want to do 99% confidence, what happens? Yeah, so my alpha actually gets smaller. So the area in the tail gets smaller, which means my Z values have to be larger. I have to go a higher number of standard deviations away now to build that confidence level that I want. So with a higher Z value, what happens to my confidence interval? Well, now my margin of error, which includes that Z value, gets larger. adding and subtracting a larger amount, my confidence interval gets wider. So what would happen is at the 99% level, because these are so close, right? It's going to push it out to be a little bit wider. I would imagine if we did that, we'd actually find out now they do overlap. So with 99% confidence, we couldn't predict this election. With 90% confidence, we could, right? This is an election, but you could apply this to, the proportion of people who use this government assistance program versus this one, or whatever you want to compare there, right? You might only be able to do it at lower levels of confidence. Is that kind of good? Yeah, I thought that's what you were kind of getting at. But kind of had to talk about this first. Any questions on this one? So I see this a lot, and just to kind of give you some context as well. Whenever you see these things like on all the news stations, like, oh, the either favorability of whatever the current president is, or if you do have an election, they'll say, we're predicting that this percent of the vote's going to go to this candidate with a margin of error of 6%, right? That margin of error is what they're talking about here. They don't want to tell you what the confidence interval is, because then it's a little bit easier to envision that they overlap, right? If I just told you, yeah, the sample proportion I found for Trump was 0.4, the sample proportion for Clinton here was 0.46. Oh, so our sample shows that Clinton's going to get more of the popular vote. Well, I mean, based off the sample, but using that sample, we know the true population proportion is somewhere in a much wider range. And if those ranges overlap, then you can't actually tell me that with that level of confidence that Clinton's going to get a higher proportion of the vote, right? And so that's why they give you the margin of error. So if you wanted to, you could construct those confidence intervals yourself, but a lot of us never go out and do that, right? It's a lot easier to sell their story. That's a very cynical view, but I think it's an accurate one. So I had the 2020 election as well. I'm just going to have this additional slide. You can work through this one if you wanted. It was kind of interesting, like to try to be able to predict these things ahead of time and see if it lines up with kind of what the end result is. So there was in 2016, everybody got the election predictions wrong. Like they screwed up, right? So they, a lot of them took some different methods. But there was one that got it right in 2016, and I think it was called, is it Reuters? I'm probably getting the name wrong, but whichever one it was, I went out in 2020 and looked at what their polling results were saying. So they had 1,200, well, approximately 1,200 registered voters. If I built a 90% confidence interval for the 2020 election, what was it, 54% said Biden. So actually, here, I actually have pretty good evidence that Biden's going to win already, just because it was above my only ranges in my confidence interval are above 0.5, right? So, but then if I looked at kind of that same poll for Trump, we had 43%. Sure enough, like that confidence interval, it's going to be much lower, right? There was like almost no chance you could reproduce this for 99%, and it wouldn't even push these confidence intervals up to be wide enough before you had any overlap. I forget exactly how far you could go, but you could like say it with like 99.5% confidence or something like that. You can then do the same thing, just use a different poll. So there was another poll that I thought might be a little bit more skewed. So I think this first one, kind of the source was a little bit more left-leaning. Not that they would build that bias in, but just in case, I used like a Fox News thing. So I used their polling results. They had a few more people, 1,500, right? So I can get a little bit narrower confidence intervals here. And then for Biden, you can kind of see here it was between 0.48 and 0.43. And Trump was just, 0.4888, 0.54912, just barely overlapped. So if you took probably the most biased poll for 2020, it was still just barely that you couldn't with 90%. You probably could say with like 88% confidence, right? Instead of it says 90, but that benchmark value of 90, maybe you couldn't have predicted the 2020 election with that high of confidence. All right, any questions on that before we keep moving? So I try to bring in relevant, interesting examples here, especially at the. You guys are in the business school, so I don't see a lot of you have a lot of interest in politics, but if you do, maybe you find this interesting. Just because you're in business doesn't mean that there's not a future career for you doing something necessarily political. whether that's, you think about all these polling companies, they're all employing statisticians, they're employing like people who now know how to interpret kind of the data or convey the analysis to kind of like the general public. So there are a lot of positions out there where this might be something pretty relevant. So what I am now going to show you is how we could do confidence intervals a little bit easier than doing it by hand, at least I think in Excel. And we can do them pretty quickly, right? Create several of them very, very fast. Okay. So I put up this file this morning called confidence intervals blank on Canvas, should be in the in-class data folder. I moved some of the old data to an old data folder. So anything that was like kind of applied to the first exam, that's all in the old folder. So let's take a look at this. So what I have on this sheet that says known standard deviation and proportion, right? So I've got a bunch of different universities we can see here, and this is just sorted alphabetically, and I don't remember why I'm missing some of these, but it's a small sample of universities. Let's see, it's 112 or 111. I've got male, female, total undergraduates, and then I have this identifier for whether or not the school had more than 10,000 undergraduates. Okay. Actually, let's do something different here, and I'll kind of show you this. So we're going to delete viewing. I'm just going to Control Shift and hit delete, right? So instead of that more than 10,000 enrollment variable, let's look at creating an indicator for whether or not the school had greater female enrollment than male enrollment, okay? So if I wanted to do this, right, I could use an if statement. So we'll start playing around with these if statements a little bit more as we do work in Excel. They're pretty powerful, but we won't use them to be too crazy. So the very first thing we're going to tell that if statement is what we're wanting to test for, okay? So if we want to create a variable where it's a 1, if female enrollment is greater than male enrollment at the university, and a 0 if it's not, okay? So we're going to say, is female undergraduate enrollment greater than the male undergraduate enrollment for this observation? Right? If this is true, comma, what value do you want to put in here? Well, if that's true, that the female undergraduate value is greater, we want to put a 1. Comma, what do you want us to put if it's false? Here, we just want to put a 0. So by using an if statement, we can very quickly create these 1, 0 variables, right? If this is greater than that, put a 1. If it's not, put a 0, okay? Any questions on that? So you go, what you want to test, comma, the value to put in if it's true, comma, the value to put in if it's false. So I'm going to then look at this cell. So this first one should be a 1. When I get this black, like thick plus sign, I'm going to double left click. And what that should do is fill this in for every single observation in my data set. So I've just created this new variable, which is the female enrollment greater than male? Okay. So the first example we're going to have, if we're trying to build confidence intervals, the very first thing we need to know is, well, what's our sample proportion or what's our sample mean? So let's look at first, and I think, I'm trying to remember what I did in the complete file. I guess I can repost it to match whatever we do in class here, but let's just use total undergraduates, right? To kind of see where enrollment is at. So I'm going to go equals average, select that first cell of total undergraduates, Control Shift, hit the down arrow. This gives me the mean kind of undergraduate enrollment at these 100 and some universities. Now, here is where it gets a little goofy. So I'm setting this up because we have to understand how to do this one before we progress to a more real world example. But let's just assume someone told you the population variance on all universities enrollments. So I had a much larger data set of universities somewhere else, and so I calculate that population variance, but we don't have that data here. So I would have to tell you what that population variance is. So it's to kind of make sure that this is my population variance. Okay. Don't worry about this cutoff for a second. I was going to use this to show you something else here in a second. So maybe we could put this down here for now. Okay. The sample size I can get by using that count function, right? It just counts the number of observations. So I'll Control Shift, Command Shift on a Mac, hit the down arrow, and it counts the number of observations I got real quick. So I've got my sample size, I have my known population variance, and I've got my sample mean. I've got all the components I need to build a confidence interval other than what confidence level do I want to build, right? What alpha value do I want? Okay. So we'll go down here. We'll build out the confidence interval. If we have time today, I'll come back to kind of using that cutoff to just think about this a little bit differently. So let's say I want to build this confidence interval. This is probably a really easy way to set this up so that it makes it a little bit, you can do it kind of quickly. So here's eventually where my upper and lower bound are going to be, right? But I first need to find my z-value. Well, how do I do that in Excel? So if we remember, what we were doing in practice is we had the area we want in the tail. We want to look it up in the table and find the corresponding z-score. So when we wanted to do that in Excel, we said we were working in reverse or kind of the inverse, right? So norm.s.inv tells Excel, okay, use a standard normal distribution. And I want you to tell me the z-score, not for alpha, but alpha divided by 2. Right? So this is going to be just like us looking up the z-score in the table. Now, one issue that's going to happen here is that if I'm using alpha over 2, I'm always looking at that left side. This value is always going to be what? Negative, all right? When I actually start entering this formula into Excel, I kind of want the absolute value, right? I want to ignore the negative sign. So I could do ABS, and that just takes the absolute value. It drops the negative sign for me, okay? What's another way I could have done this? It's a little bit tricky. I don't think I've shown it. I don't think I mentioned it earlier when we were looking at the examples. But what I really want in this cell is that positive z-value, right? Well, I know that there's alpha over 2 to the right of the positive z-value I want, which means I know the area to the left would just be 1 minus that. So what I could have done, instead of using this absolute value, I could have done norm.s.inv and then done 1 minus alpha over 2. And then it gives me that value, right? Because it gives me that positive value. So I could use either one here. Doesn't really matter. Got our z values. Notice they're a little bit different than we looked them up in the table because we can be more precise. Right? I don't have to round things to the second decimal here, or I don't just find the value that's closest to the probability I want in the middle of the table. I can find the actual value when I'm doing this in Excel. So from here, it's basically just using Excel to be a calculator. Now, I think it's easier to calculate the intermediate step, right? That standard deviation of my sample means. So, oh, do I not have a cell for it? We can do it. We can do it down here. So I'm going to do standard deviation of my sample means. I'm going to calculate this down here. Well, all that is the square root of whatever my population variance is divided by my sample size. So notice I don't even have to see that equation. I'm just clicking on the values I want, right? And it's going to, oh, get out of here. Nope, stop. Okay. Right, so all I'm doing is taking the square root of that population variance divided by my sample size. So I have a pretty big standard deviation on the sample mean, but I'm also dealing with a variable, right, that's in the thousands. So that kind of makes sense, right? And I have a lot of variation in school size, just we kind of intuitively know that. Right? Any questions on that? Right, so all I'm doing, let's not get too lost in this kind of like, oh. So all we're doing there, right, is taking the square root of the original population variance that was given to me, and we're dividing that by our sample size. Right? So kind of like when we were doing this by hand, it's just now we're clicking on the cells that have those values in them. Right? Any other questions? No? All right. So from here, we're just using Excel to be our calculator, right? To get my lower bound, I'm going to take the sample mean I found. So I click on my sample mean. And then I'm going to subtract my margin of error, which was the Z value for that specific level of confidence, right? Multiplied by the standard deviation of my sample means. Right? So this is what I want. Now I could copy this down and get the lower bound for the 95%, lower bound for the 99% level, right, pretty quickly. The problem is the only thing I really change when I'm looking at different confidence levels, right? I'm still basing it around the same sample mean. The standard deviation of my sample mean hasn't changed. The only thing that's changing is how many standard deviations out I'm going. So the only thing I want to change when I copy this down is going to be that Z-score. So everything else, I'm going to hit F4 or Command T on a Mac and freeze. Now when I copy this down, I get my 3 lower bounds for these 3 different levels of confidence. And notice, as I want to say things with a higher and higher level of confidence, my lower bound should be getting lower and my upper bound should be getting higher, right? I should be getting a wider interval. Sure enough, my lower bound is getting lower. Hopefully, when I do the upper bound, it's getting larger. So I think the easiest way to do this, you could try to freeze some things, copy this over. If you double click on the cell so you can see the formula, I'm just going to highlight this, copy it. To get out of the cell, I'm just going to hit enter, right? I'm then going to go to my upper bound, paste that equation, because I want the exact same thing, but instead of subtracting that margin of error, I want to add it, right? It's the only difference when we were kind of working this out by hand. I subtract the margin of error to get my lower bound, I add it to get my upper bound. Okay. Questions on this? So now, when I copy this down, it updates the Z value, keeps the other things the same. My upper bound is getting larger. I've now got my confidence interval for my sample mean, not just one confidence interval, but I've got the 90, the 95, and the 99% confidence interval. Okay. Any questions over anything there? Okay. So we got 2 minutes kind of left here. I think I'll save for next class. We'll do a very similar thing. I'll walk you through how we do it in Excel. And after next class, I'll splice the videos together and upload them as like a separate Excel kind of help on building confidence intervals. But we'll build a confidence interval for a sample proportion. And let me save this real quick before I forget. So we'll kind of pick up where we left off. Other than that, kind of nothing new here. We got the homeworks to finish up. I believe they're both due at the end of the day on Friday. So if you have any questions over those, I'll be around tomorrow kind of for normal office hours, 11 to 1. If you need to meet a different time, email me and we can set up a time. Okay. All right. I will see you guys on Friday.